All right, we are going to continue with our catalogue of series tests. In fact, here's something I prepared earlier. This I drew up last time, and this is the summary of all the tests. Here are the tests that only pertain to series. We already did these four, so I've still got to do the integral test and the alternating series test, as well as the tests that apply both to improper integrals and to series. So I'm going to do these 6 tests, and that probably take about an hour. And then for the remainder, I'm going to do an introduction to power series and Taylor series. I'm going to attempt to do more than what at least Math 104 does in a way. I'll try to give you the big picture first, and then next time we'll get our hands very dirty and do a whole lot of problems. So I kind of want you to see the big picture of how all this stuff works. So in any case, before we talk about power series and Taylor series, as I say, we've got a bunch of tests to do. So picking up where we left off, I would like to start with the integral test. Okay, so this is not a test for integrals, it's a test for series. You can read about it in my book in 22.5.3 and 23.5. That's the theory, and that's how to solve problems. Okay, now, before I tell you what the test is, let me tell you, you can actually use this a lot of times to solve certain problems, but most of the time, you don't really need to. In fact, the only time that you really need to use this, in principle, is when your series, so use when the series involves 1 over n, exactly that power, and a logarithm somewhere. There may be other examples, but this is by far the most common example or paradigm of when you need to use this integral test. So a prime example would be the series that we actually looked at the end of last time, 1 over n log n. That series, I'm starting at 2, by the way. Remember, it doesn't really matter where you start these things, but if I do start at 1, then log of 1 is 0, and we'll have a stupid term that's 1 over 0. So I'm just avoiding that. In any case, we saw last time that the ratio test fails to give us any useful information in that case. When we tried to use it, we got a limiting ratio of 1, and that doesn't tell us anything. So I said use another test. Well, I'm going to use the integral test. Now, in order to, I'll tell you what the test is, and then I'll give you a bit of justification. It's a nice little test. What it says is, you know, instead of a series, you can write down an integral. So you write down this integral. You just change the n to an x. And then you have to put a dx. And instead of summing from 2 to infinity, you integrate from 2 to infinity. So consider this integral. Okay, so you've transformed the problem to an integral. Now, for this to be valid, there is one important condition that you need to check. Note that the integrand, 1 over x log x, is decreasing. In x. That means when x gets larger, 1 over x log x gets smaller. How can you see this? Well, you could differentiate it and show the derivative is negative. Not so bad. But in fact, even easier is that x is increasing, log x is increasing, right? Goes up. Therefore, x log x is increasing. If you multiply two increasing functions, you surely get an increasing function. And therefore, the reciprocal is decreasing. That's a little bit of justification without using any calculus. Common sense, really. Okay, now that is an important condition because the integral test requires it. But in any case, having said that, take a look at this integral. We want to just see whether the integral converges or diverges. Well, we've already looked at this problem a few weeks ago. We saw that the way to do it, given the tricky relationship between log x and 1 over x, is to substitute. We put t equals log x, so dt is 1 over x dx. Also, we've got to pay some attention to the bounds. when x equals 2, t is actually the logarithm of 2. As x goes to infinity, x can't actually equal infinity, but as x goes to infinity, t, which is log x after all, also goes to infinity. So that this integral in t land becomes the integral from log of 2 to infinity, 1 over t dt, because the dt is the dx over x, or 1 over x dx. And this diverges by the p-test. So the integral diverges, and the integral test says, therefore, the original series diverges too. Therefore, by the integral test, series, or original series, you can write it out again, whatever, n equals 2 to infinity, 1 over n log n diverges as well. Okay, so notice that the reason that the integral was more successful than the series is because we could do the substitution. You're allowed to do that substitution. There's no such substitution method for series. So that's the only real reason to transfer to an integral, is if you're going to do a substitution. You can transform to an integral to do a p-test or a comparison test or any one of these things, but soon we'll see there's versions of all these things for series anyway, and you're just sort of adding in an extra step if you do this. So for a general question that doesn't, if you don't do a substitution, there's probably no point in using the integral test. On the other hand, for this question, there's no other way of doing it. Or no other easy way, that's for sure. You can't use any of these other tests. All right, so what is the integral test in general? Let me just summarize it, having used it. It says that if f is a decreasing continuous function, then the series f of n from n equals anything, I sometimes put a little squiggle there, it doesn't matter where you start. Oh, what the hell, I'll call it an a. Then the series and the integral either both converge or both diverge. So practically, whatever the integral does, the series does as well. So this sort of justifies what I was saying about series at infinity being very similar to improper integrals with problem spots at infinity. Series, infinite series, I should have said, and improper integrals with problem spot at infinity. Okay, so in this case, we're using the both diverge. But it's pretty easy to come up with examples that both converge. An example is that we already saw, and this was a few weeks ago, so I don't blame you if you forget, but we saw that this integral, 1 over x log x to the power 2, say from 2 to infinity, converges. And actually, I'll leave that to you, but you know, if you do the same substitution, the only difference is you get a 1 over t squared instead of a 1 over t. And that converges by the p-test. So actually, by repeating the same details, you can see that this converges as well by the integral test. So I'm sort of giving you a very brief version of it because I want to do a lot of other stuff. But just go and repeat the previous argument and convince yourself that that series converges. Question? Well, most things are continuous, at least if they involve x's and logs and stuff like that, right? We've done that. But you see, in this case, look up that example there. How did I tell it was decreasing? Well, as I said, you could differentiate it. If you differentiate a function and its derivative is always negative, it's decreasing. Actually, even if the derivative is 0 for a bit, you're okay, as long as it sort of doesn't go up. Or you can do what I did over here, which is I looked at the pieces of it, and they were all increasing, and then the reciprocal was decreasing. So that's just sort of a prototype. Well, okay, so the question, log x is increasing. How would you tell that log x is increasing? Yeah. Right. Yeah, I mean, look, the aim is not to get too bogged down here about proving something is decreasing. On the other hand, you should state that it's decreasing and give a little bit of justification. Most of the time, it's fairly straightforward, as it is in this example. Right? Otherwise, as I say, you could differentiate it and show that it's negative if you really want to nail it down. It's just a bit of a mess. I mean, how would you show that 1 over x is decreasing if you don't believe it? Just take the derivative of 1 over x, you get negative 1 over x squared, which has to be negative. And that really clinches that 1 over x is decreasing. All right, now, I'm not going to spend much time justifying the test. Let me just show you a picture of why it works in this case, because it's kind of interesting. Here we're trying to take the function 1 over x log x. That's a decreasing function. It looks something like this. Okay, so what we want is the series beginning at 2. Now, if you go up to 2 on this function, you get 1 over 2 log 2, which is the first value of the series. Now, suppose I draw a rectangle of width 1 here. What's the area of that rectangle? Well, the width is 1, so the area is 1 over 2 log 2. That's the first term in our series. If I do the same thing at 3, and then at 4, 5, then I've screwed up. Okay, forget what I just wrote. Let's try again. Sorry about that. I've gotten the whoop-de-doo case without even intending it. Let's do it this way. Okay, instead I want to have the same thing. I start at 2, and I go up, and I get 1 over 2 log 2. I actually want to take the rectangle this way. Same thing, though. The area of this is 1 over 2 log 2. Okay, now let's take this rectangle. The height is 1 over 3 log 3, and the width is 1 again, so that's 1 over 3 log 3. I do the same for 4 up to 5. That's 1 over 4 log 4, and so on. I'm going to take an upper sum where all the rectangles are width 1. Now, if I add up all these quantities, I just get the series. 1 over 2 log 2 plus 1 over 3 log 3 plus 1 over 4 log 4. That is the actual series that we are interested in the first case. Now, the integral looks like this. And as you can see, it's contained within the boxes. So actually, the boxed area, which is our series, is bigger than the blue area, which is our integral. But we've seen that that diverges. So by comparison, the series diverges as well. So the integral test is just a clever comparison with an upper sum. But what if it converges? Well, then I kind of screwed up. I started doing the convergence one. For the convergence, you use the left-hand version that I had started with, and then use the comparison test the other way, and it works. There's more of an explanation in section 22.5.3 of the book. But that's basically what's going on. So it's not just a mystic thing. There's a reason why it works. There's a proof. And the beauty is you can use the integral test without having to draw this picture and do a comparison. It just works. By the way, the reason you need it to be decreasing is that, I could thwart you by having these ridiculous big humps in between these values. And that could make an integral that would have otherwise, say, converged, diverged, because you have these huge sort of humps in there. And the series only samples the values at 2, 3, 4, 5. It doesn't know what the function does in between. So that's why you need to have the decreasing. Otherwise, the integral test could fail. Question?
Can't you just say that 1 over x diverges the lowest limit of divergence in any function which would be smaller by the factor of n will therefore converge?
So you're saying that 1 over x is the smallest thing that diverges. But this is not true, because when you put 1 over x log x is actually bigger than 1, so 1 over x log x is smaller than 1 over x, and it still diverges. So do not think that 1 over x is the smallest function that diverges. It's not. There is no smallest function whose integral or series diverges, okay? There's a gray area. There are series that converge, there are series that diverge, and there's no barrier. Just like there's no smallest positive number. There's no smallest positive number. Whatever you say is the smallest, I can do better by halving it. Okay? The same thing. There's a very fine spectrum, and you can keep zooming in, but there's no last function. Okay? So get that out of your mind as a possibility. You have to do things like this. Okay. Any other questions about the integral test before I move on to the other tests that are in common with both series and improper integrals? Well, in that case, I don't intend to spend a huge amount of time on the tests in common. We've got a comparison test, a limit comparison test, and a p-test to worry about. We've also got an absolute convergence test, but I'm going to talk about that a little bit later. So I want to look at those 3 tests. And by the way, I should mention 22.4, 23.6. This is the theory, and 23.6 are the examples, just for a reference for my book. Now, we know these tests for improper integrals, and the beautiful thing is that the tests are basically the same for series. You just have to write it in a different way. So, in fact, any problem that you can use these tests for, the integral version has the same solution apart from the notation. So, luckily, this is all in common with what we've done before. But let me just say what the tests are. Let's start off with the comparison test. And I'll just say it really quickly, because we've done it, as I say, for the improper integrals. So, in each case, for this paradigm to work, we're dealing with the series AN. It doesn't really matter where it starts. 1, 0, 10. And then I'm going to assume all the terms AN are positive, or at least greater than or equal to 0. If there's negative terms, you have to take special care, and that's what I'm going to talk about immediately after doing these 3 tests. All right, so we've got this comparison test, limit comparison test, p-test. Series, all the terms positive. Here's what the comparison test says. Okay, so there's 2 versions. Suppose you think the series diverges. Series, the original series you have, diverges. Find a bigger series. No, I keep getting this the wrong way around. Find a smaller series which also diverges. I.e., you want AN to be bigger than some other BN, and no cheating by picking negative series. This still has to be positive. So find this so that the new series that is simpler, and it doesn't matter where it starts, diverges. Then the series that you want is bigger, n equals whatever, n equals whatever. The series you want is bigger than your new series, which supposedly diverges. So you're trying to find something, you're adding up a whole lot of things, add up a whole lot of smaller things, still get infinity. You are then floating above infinity, which means you're also at infinity. Well, how did you do it for integrals? How do you find something that's smaller? We did it for integrals by learning how functions work. Right? For example, well, it's easier to find something that's bigger, but I told you, for example, this rule, right? That log of n, or log of x, I stated it, is less than c times any power of x. There's something that I did, no matter how small. So, for example, if you have a sum involving 1 over log n, You could use, if it was necessary, the fact that this is greater than 1 over Cn to the alpha, where you get to choose the alpha. That's an example. It's not attached to a question, but since the question was, how do you know? What you're looking for is simpler functions, and in our case, they're all going to be 1 over n to the p. We're going to use the p-test. So just bear with me here, and you'll see by example. But again, just think about improper integrals, and there's nothing new here. To get the convergence, if you think it converges, find a bigger series. This time it's a bigger series, which converges. So now we're trying to find a Bn that's bigger. Find this. And you want the new series to converge. So then you have the sum an from wherever to infinity is less than the sum of Bn, which is presumed to be finite. Therefore, this converges after all, as you want. Now, if you look back at the statement that I wrote down of the comparison test for improper integrals, you will see that it's basically the same. I've just changed integrals to series. X goes to n. Instead of writing f of x and g of x, I wrote an and bn. Okay, so before I give examples, I'll just state the other two tests, and then we can do a bunch of examples. And you'll see how similar they are to improper integrals. The limit comparison test, to set this up, we need a twiddle notation. We need the concept of an twiddle bn as n goes to infinity. Okay, what should that mean? If an actually equals bn, then the ratio an over bn would actually equal 1. But that's a little bit too much to expect. After all, they don't have to be equal. They have to be almost equal, in a way. So it's this. The limit of the ratio is 1. So this means, I'll put them in quotes. Okay, again, how do you know what this is? Well, we did a whole lot of relationships like that involving polynomials and involving some trig functions, all that sort of stuff. So as a simple example, we know that n behaves, or let's say n plus 3 is asymptotic to n as n goes to infinity, because the limit of the ratio n plus 3 over n is the same as 1 plus 3 over n, so that limit is 1. So whenever the limit of a fraction is 1, the numerator twiddles the denominator. And in this case, n is always going to infinity, because in series that's the only place the problem spot can be. And so you need a limit as n goes to infinity. Now, given that, here's the theorem. Here's the limit comparison test. So if you want to understand this series, so find, that's the series we're working with, n equals something to infinity. Find an twiddles bn, so find this, where bn is simpler, then the sum bn does the same thing. Well, let's say the sum an does the same thing as bn. What do I mean by the does the same thing? I mean converges or diverges. Now, if bn, that series diverges, then so does an. If it converges, the an series converges, but not necessarily to the same thing. You just know whether or not it converges. So that's the same as it was for the integrals, right? The limit comparison test, you're looking for twiddly sort of stuff, and then you check the new one and see if that converges. Now, we get to the question of how do you know what functions to choose? Well, the p-test gives you a rich source of functions, and luckily there's only one version for series, because there's only a problem spot at infinity. No matter where you start, 1 over n to the p converges if p is bigger than 1, and it diverges if p is less than or equal to 1. And this is the same as p-test for improper integrals at infinity. Not at 0. That was the other form of the p-test. We don't need it here. Okay, those three things together are enough to solve all of the problems in the category where they can be solved, namely the ones where they would also work for improper integrals. So we better look at a whole bunch of them. Any questions about that theoretical part, or at least the catalog of the test there? If you have one, shout it out, please. Okay, where did my page go? I think it's over here. All right. Here's an example. N equals 1 to infinity. Sum 2n squared plus 3n plus 7 over n to the 4th plus 2n cubed plus 1. All right. If you use the ratio test, you will find that you get a ratio of 1. I leave it to you to try it out. The ratio test does not work. You have to do something like this. Look, 2n squared plus 3n plus 7, the largest term of a polynomial dominates when n goes to infinity. You can prove this by taking the ratio. You'll get 1 plus smaller stuff that goes to 0. Stuff with n on the bottom. Powers of n on the bottom. Similarly, n to the 4th plus 2n cubed plus 1 twiddles n to the 4th as n goes to infinity. These things deserve proofs when you write it out. I'm trying to save a little bit of time by not writing it. We've done this exact sort of computation for improper integrals, as I said. Therefore, the ratio of these two things, which is what we care about, behaves like 2n squared over n to the 4th, which is 2 over n squared. Okay, so consider this series. New series. N equals 1 to infinity, 2 over n squared. Well, the 2 is not very important. That's just a constant. Constants come out of series just as they do integrals. And you get 2 times the sum of 1 over n squared. Well, does that converge or diverge? Converges by the p-test. After all, 2 is bigger than 1. Converges by the p-test for series. Well, therefore, by the limit comparison test, the original series converges as well. That's the whole solution, although, as I say, I would like to see a couple of limits to justify those two, and then this one will follow. All right? How different is that from the improper integral from 1 to infinity 2x squared plus 3x plus 7 over x to the 4th plus 2x cubed plus 1 dx? Suppose that was the problem. How different is that? It's not different at all. The answer is exactly the same. Here you have x's, and instead of considering the sum, you would use the limit comparison with 2 over x squared. but that converges by the p-test. So you see, it's the same problem. It's just wrapped up in the skies. It's a different, series instead of an integral. You definitely don't need to use the integral test to convert this into an integral. You'd have to worry about the decreasing business. But even if you did, you'd just be writing a few extra words that you don't need to, because you can just use the native series versions. Any questions about that? Okay, fairly straightforward. What if the sum goes from 0 to infinity of the same thing? How much difference could that make? Well, if you use the same argument and you start writing down, consider the sum from 2 over n squared, n equals 0 to infinity, well, that's a silly series to write down. Because the first term, when n equals 0, is 2 over 0, which is undefined. So that series doesn't even make sense. You just never say consider something that doesn't make sense. So what do you have to do? Well, if you really want to be anal about it, you split off n equals 0 first. So if you split off n equals 0 and you plug in 0, you'll get 7. Right? You get 0, 0, 7, 0, 1. So you'll get 7 plus the old sum. We did a very similar trick for improper integrals. We split them up into 2 pieces, one of which was benign. So now we get this new sum which doesn't have this spurious problem spot at 0. So now you can compare this with n equals 1 to infinity, 2 over n squared. So it's kind of silly stuff, really, but that we've already done. That was the previous example. How much difference does it make to add 7? If this is a finite number, adding 7, it's still finite, still convergent. On the other hand, if this was infinity, 7 plus infinity, it's still infinity. The first term doesn't make a difference. I'm just saying, as a cautionary tale, if you said this converged by the p-test, you would be wrong, because it doesn't make sense. On the other hand, you'd probably only lose a point or 2 out of 10. Maybe you wouldn't lose anything. I'm just trying to stop you from... I don't want you to write down things that don't make sense, really, even though we know what you mean, and if you leave out the first term, you know exactly what you're doing. So just take a little bit of care in that example. Let's look at this example. 2 to the minus n, n to the 1,000. Well, this is very similar to an example that we saw in integrals. By the way, the ratio test does work for this, and it will show you that it converges. I'll leave that to you as an exercise. Let's just do it using comparison. You may recall from the improper integrals that I said you could do e to the minus x is less than constant over x to the n, and you can pick the n here. It can be really large, and that's still true. It's also true if you replace e by any other number bigger than 1. So for example, 2 to the minus n is less than c over, well, now you've got to be a little bit careful. Let's do this. 2 to the x is less than c x to the n. Well, now we've got to change our variables. Maybe I'll make this a capital N so we don't get too confused. So the version that we need is 2 to the minus n is less than c over n to any power you like. Now, if I pick a power that's at least one, well, more than 1 more than 1,000, so say 2 more than 1,000, it's the same trick we did before. This is all sort of rambling here. What I actually need for this problem is that 2 to the minus n is less than a constant over n to the 1,002. Or I could pick any bigger number. Anything bigger than 1,001 will work. If I do this, I can do a direct comparison on this series and say, well, there's some constant over n to the 1,002. That's such a big power that it kills off the 1,000 with some room to spare. The constant comes out, and we're left with 1 over n squared. And again, this converges by the p-test. And this is all comparison. So the original series converges by the comparison test. Everything is positive. And if you think I'm sort of doing it very quickly, I agree, I am. But I'm only doing it quickly because I have confidence that you could do already this improper integral, as we did, in fact, using the same method of comparison. It's just x integrals. Now we're dealing with n's and sums. Okay, so again, not particularly new. All right, there are a bunch more examples in 23.6, but I don't have much time to go over them. I'll do one more. Actually, I'll do one more. Most of the improper integrals that you've looked at, by the way, can be changed into series, and the solutions will be the same. The exception is that 1 over n log n type of series that we needed the integral test to convert it back to an integral. All right, so here's another example. Sum n equals 1 to infinity, sine squared of 1 over n. Now, in this case, when n gets large, what happens to 1 over n? Small, near 0. So we're taking a sine of a very small number. You may recall that sine x twiddles x as x goes to 0. So, after all, the limit of sine x over x is 1. So that's a classic thing. Again, we did this for improper integrals. If we let x equals 1 over n, then we have sine 1 over n twiddles 1 over n as 1 over n goes to 0, i.e., as n goes to infinity, or even minus infinity. So, sine 1 over n behaves like 1 over n. Let's square both sides. That's allowed. You can multiply, divide. You can't add or subtract, but you can take powers. Sine squared 1 over n twiddles 1 over n squared as n goes to infinity. So that is the crucial fact, and then you can use a limit comparison test with a much simpler sum. Again, it's 1 over n squared, which converges. P-test. I've left out a lot of details, and you have to fill it in and thresh it out and make a proper solution out of it. But notice, again, that the solution of this problem, sine squared 1 over x dx, is the same. You use limit comparison test with 1 over x squared. Okay, so we're on familiar territory. And so it's doubly important, in a way, to know improper integrals, because some of the series problems are really the same thing as improper integrals. Okay, so it's sort of a double whammy. Of course, there are the other series problems that involve these other tests that don't have integrals. There's no integral factorial version that we are aware of. In fact, there is. It's called the gamma function, but it's not, doesn't belong in this course. So, you know, in this particular case, if you see a sum with factorials, don't try to do this stuff. Do the ratio test, as I said last time. All right. So, again, go back over improper integrals and change any example, almost any example, unless you did a substitution in the solution. If you change the example and its solution to a series with n's instead of x's, you will get a valid series problem and a solution. Okay? Any other questions about that before I go on to series with negative terms? Okay. Well, all those tests involve only positive terms. In fact, the ratio test and the root test, as I presented them, involve absolute values, and that sort of makes everything positive. So I haven't really said much about series with negative terms. Luckily, the situation's pretty similar to improper integrals, but there is one important exception called the alternating series test, and I'll have to talk about that. But first, so suppose you have negative terms. Okay, here are some possibilities of how to handle it. If all the terms are negative, that's not a big deal. Pull out a minus sign, a factor of -1, if you like, and everything becomes positive. So the series can be written as negative something, where these are now positive. So I'm going to just pull out the minus sign. And then I can use all my other stuff. So I have a nice little example that's also a limit comparison type of problem, or actually a comparison test. So consider this series. Log 1 over n, 1 over root n. Okay, well, I kind of wrote that as a trick thing. I mean, the fact is, log 1 over n, I should really just write, to save myself a problem, minus log n. It's log 1 minus log n, and log 1 is 0. So if I wrote it like that, then you could clearly see that all the terms are negative. But that's okay, you know. I'll just pull out the minus and look at this series, log n over root n. Okay, this I can use comparison, because everything's positive. And if this converges, by the way, then the minus sign, it will still converge. It will just converge to the negative of the other thing. And if this diverges to infinity, well, then this will diverge to minus infinity. So whatever this does, the minus sign doesn't really change very much. It doesn't change the convergence or divergence. We still have to deal with this, by the way, and that's not such an easy problem. I did do a similar problem with integrals, improper integrals, but I'll repeat it in this case. What would happen if the log n was not there? Would it converge or diverge? 1 over root n. That's the same as 1 over n to the half. A half is less than 1, so yes, less than or equal to 1. It would diverge. How much difference does the log n make to that? It shouldn't make much of a difference. But in order to really deal with it, in fact, it's on the top. It's on the numerator, so it actually even makes it bigger. Consider this. I'll write it as n to the half. How small could log n possibly be? What is the value of log n? It becomes log 3, log 4, log 5, log 6. What's the smallest that log n could possibly be in this series? Since log is increasing, log 3. So log n, so if n is bigger than or equal to 3, log n is bigger than or equal to log of 3. So actually, I'll just do a really simple comparison with log 3. Log 3 is just a constant. So I'm going to pull it out. It's quite irrelevant. That series diverges. This is infinite. So log 3 times it is also infinite. So this actually is bigger than something that is infinite. Well, bigger than or equal to, it must be infinite. So this diverges by the comparison test. If you don't like the log 3, you can replace it by just a c. C being a constant, but log 3 is what it should logically be. Anyway, so this diverges, in fact, to infinity, because it's all positive. So this diverges to minus infinity. Can't diverge to infinity because it's negative. These series with all positive terms have to diverge to infinity if they diverge at all. I said this last time. If you have positive terms, the only way you can diverge is to infinity. There's no oscillation possible. Right? You're just going in one direction, getting bigger and bigger. Infinity is the only way. There's no sort of oscillation. If they're all negative terms, minus infinity is the only way you could diverge. Of course, you could converge. Things are much simpler when everything is positive or everything is negative. Any questions about that? All right. Okay, so that's one possibility. What else have we got? Well, we have this nth term test, which I talked about last time. Remember, that says that if the terms of the series do not go to 0, the series must diverge. And it doesn't care if they're positive or negative. So here's a sort of silly example. Sum from 1 to infinity minus 1 to the n times n squared. This is certainly positive sometimes and negative sometimes. In fact, it's alternating between positive and negative. The first term's actually negative. Minus 1 to the 1 is minus 1. But when n is 2, it's 1. When n is 3, minus 1. So outside of this positive quantity n squared, we have an oscillating 1, minus 1, 1, minus 1. So if I'm standing here at 0, the terms of this series are, first one is minus 1, back 1. The next one is plus 4, 4 steps. The next one is minus 9. And then plus 16. How can I possibly start homing in on one particular patch when I'm running back and forth further and further away like a maniac? I can't. Even if I was only running back and forth like this. And so on. I still wouldn't converge to one spot. The only way I can converge is if my steps become really, really dainty. Right? So this actually limit of the term itself does not exist. It's certainly not 0. In particular, the limit is not 0, so the series diverges. Again, if you replace the series by a limit and you get anything other than 0, diverges. Doesn't matter about the positive, negative. That's the nth term test. We talked about it last time. So all I have to add is that sometimes you can solve these problems involving negatives directly by the nth term test. But often you can't, and you end up with the absolute convergence test. So this is likely the same or very similar in series and integrals. Here's what it says. So suppose you have a series that you're interested in, where now the ANs are both positive for some n's and negative for the others, or 0. Consider this. It's a series, but all you do is take absolute values of each term. Well, that's a positive series. All the terms are positive, so you can use comparison, p-test, limit comparison, and ratio, any of the tests if you like on this. If this converges, if this new series converges, so does the original. That's what the test says. The same as improper integrals. Okay, a few comments. First comment, in this case, we say the original series converges absolutely. So there's a special name. If I say a series converges absolutely, what I mean is that if you took the same series but whacked absolute values around each term, and it still converges, well, actually, that's what I mean. If you did this, then the new series would still converge. Okay? So, in fact, you know, any series that we wrote down that's all positive terms, such as, to save me from writing another one, that one up there, right? Sine squared 1 over n. Certainly all the terms are positive. Well, that converges, as we saw, so it also converges absolutely. It's not very interesting because all the terms are positive. Where it's interesting is where some of the terms are negative and some of the terms are positive. So, let's look at an example. So suppose we consider classic example, sine n over, let's do n cubed for variety. Sine n over n cubed. Well, the n cubed is certainly positive because n is positive, but sine, remember, it's sometimes positive, sometimes negative. So this is not always positive. We cannot use the comparison test directly on this. So instead I say consider the absolute version, which is the same except I whack an absolute value around the sine. Okay, well this clearly equals the absolute value of sine n over n cubed, because after all, n cubed is positive when n is positive. Sine n is less than or equal to 1. So we're going to use direct comparison with 1 over n cubed. And we're allowed to do this now because everything is positive. This is a comparison test in here. It needs everything to be positive. You cannot do comparison test on the original series because sine n could be negative. It's not allowed. So in any case, this converges by the p-test. Therefore, this series the new one we looked at converges by comparison test. It's smaller than something that also converges. Therefore, the original series not only does this converge, it converges absolutely. And implicit in that statement is the notion that it actually converges, and that is by the absolute convergence test. So we have this special terminology for converges absolutely. Now consider one more series, and this is a really classic series. Minus 1 to the n over n. Well, consider its absolute version. So we'll take the absolute values, and the minus 1 to the n is just either 1 or minus 1. So when you take the absolute value, it forgets which one it is and just reduces it to 1 over n. Does that converge or diverge? It diverges by the p-test. Okay. So, what can you conclude about the original series? Nothing. You cannot use the absolute convergence test to show that something diverges. You cannot use the absolute convergence test. All you can say is that this does not converge absolutely. But the amazing thing is, it may still converge anyway. Okay, to explain why it actually does converge, we're going to use the alternating series test, and then that's all we have left to talk about in series. And then we can talk about power series and Taylor series, which is something else altogether. Now, here's what I want to get across. Let's look at 1 over n. What are my steps? I start at 0. I step 1. I step a half. I step another third, a quarter, a fifth. My steps are becoming really, really tiny. And it's hard to believe, but if you leave me for long enough, I will make it to that wall. And if the wall wasn't there, I would make it a mile down or 10 miles. And no matter how, I'm taking so many tiny little steps, and somehow, out of these tiny building blocks add up, I get to anywhere. Doesn't matter how far away. If you give me long enough, it's going to take a really long time. But I will get there. So that's 1 over n diverges. It's amazing, but it's true. That's what it means. So even though the step sizes go to 0, nth term test also is useless, because the series diverges, but it's got nothing to do with the fact that 1 over n goes to 0. It doesn't mean that it converges. It's a diverge. Now, what about this series here? Well, it's now alternating. The first term is minus 1. The second term is a half. So I'm not actually back to my starting point. The next term is minus a third. I'm going to keep my right leg there for reference. Okay, I know you normally film the board, but I hope you're getting the feet this time. Good. So now I've gone back a third. Now I've got to go forward a quarter. So from here, I'm not actually to where my next point was. So I'm now here. And then back a fifth. Well, that's not as far back. Then forward a sixth. And somehow my legs are getting closer and closer together to something. And I am actually converging. Here it is in blown up form. I start here, I go back, I go forward but not as far. I go back but not as far. I go forward, again, not as far. And I will be converging to something. Okay? Does that make sense? You're embarrassed. You're just embarrassed. Yeah, but next to you, she's like, oh my God, what's he doing? Is that true? She's not judging me. Good. Oh, the shoes. Yeah, they're falling apart. I admit it. I'm a mathematician. I'm not supposed to have any fashion sense. Come on. Look, the thing is, if you were judging me, then you would be holding up some sort of placard with a number on it, and given the subject matter, it could be minus infinity, which would be pretty bad. So, that is all I have to say. At least about that. Now, here's the deal. If your series is not absolutely convergent, so you've tried all these other things, and you've shown it's not absolutely convergent, which I'm now going to write abs convergent, try the alternating series test. And that's just a generalization of what I was talking about in terms of this back and forth. Now, by the way, it has to be alternating for this trick to work, or else I could end up, I don't know, going forward or backwards in the long run. The other thing is, and you're going to have to put up with some more tap dancing here, I'm afraid, here's the deal. If my forward steps are not always bigger than the next backward step, and the next backward step not always bigger than the next forward step. So in other words, if my steps are not getting smaller and smaller, I could take a big step forward, a smaller step back, a big step forward, a smaller step back. Even if my steps are getting smaller and smaller, but just not monotonically, I could actually end up advancing and not converging. Also, if my steps are not actually going down to 0, the nth term test will kick in. I could be going like this. But there'd still be this barrier in between and not converge. So somehow, I need to alternate. The steps need to get smaller and smaller, and they need to go down to 0. If all three things happen, then my legs will go together, and I will find that I converge to somewhere. Let's write that down. Here's what the test says. If terms are alternating, and the terms in absolute value, i.e. an, are monotonically decreasing. Let's just say decreasing. I haven't talked about monotonically. Let's just say decreasing. That's good enough. And the limit of the terms is 0. This is the same thing as saying you don't even need the absolute values. It's the same thing. Then the series, again, it doesn't matter where it starts, converges. Okay, so let's look at this example that we've been dealing with. 1 over n minus 1 to the n, in fact, over n. All right, let's check the three conditions. First of all, it's definitely alternating because of the minus 1 to the n term. Okay, a series is alternating if it looks like minus 1 to the n times a positive number, or minus 1 to the n plus 1, or something like that. So you don't need to talk about it very much, just notice that it's alternating. Also, the absolute value of each term looks like this. And that's decreasing in n. My steps in size, not backwards or forwards, but just the actual size of the steps, is decreasing. And this is very similar to your question from before. How do you see that something's decreasing? Well, n is increasing, so 1 over n is decreasing. Okay, so just to reiterate here, I take the absolute value to get rid of the alternating. If you get rid of the minus 1 to the n and just look at the rest of it, it needs to be decreasing in n. And finally, the limit of this is 0. Therefore, the series converges. By the alternating series test. Okay, so we've just used a test, which I haven't really proved other than by doing some tap dancing. It's not really a legitimate mathematical proof by footwork, but nevertheless it shows the idea. And if you really want to see the proof, it is in my book, and I'll get the page reference in a sec. For the moment, though, that is the proof that this series converges. Now, we know it does not converge absolutely, because we looked at it before. We said, if it weren't for the minus 1 to the n, if that was just a 1 on the top, it would diverge. And yet, with the minus 1 to the n, it converges by this test. So we say, since it does not converge absolutely, but it does converge, we say it converges conditionally. Converges conditionally. Conditionally means it only converges because of the minus 1 to the n. Conditional on that. If it weren't there, we'd be screwed. It would diverge. So what's the moral of the story? I feel like I should summarize parts 3 and 4, as in the absolute convergence part and this alternating series test, into one sort of summary wrapper. And here it is. If you do have a series which is alternating, so if you have a series that looks like this, where these are positive, or 0, so this is alternating. And another form, just so you are not confused, let it be known that n plus 1 will do. That's also alternating. Or you could have n minus 1 or something like this. But not 2n, by the way. Minus 1 to the 2n. Just as a little comment, is always 1. Minus 1 to any even power is 1. So, well, if it's negative, then it's not going to be alternating anymore, is it? I mean, if it's sometimes negative, if it's always negative, it will still be alternating. But if it's always negative, you could pull out a factor of minus 1 and write it like this. So every alternating series can be written in the form minus 1 to the n times positive terms, or minus 1 to the n plus 1 times positive terms. Okay? So, if you have an alternating series like this, first, check the absolute value version. Which, after all, is just the sum of the ANs. First, check the absolute version. If this converges, then the original series converges absolutely. And you stop. You already know that the original series converges. In fact, it really converges, powerfully converges absolutely. Otherwise, try the alternating series test. And remember, you have to check three things. Alternating, we already know. The absolute value of terms has to decrease. And normally you can just say it, but at least try to justify it a little bit. And finally, you need the limit of the absolute value of terms as n goes to infinity to be 0. And if these are all true, if so, the series converges conditionally. Why conditionally? Because you've already checked that it doesn't converge absolutely. Now, what if it doesn't converge absolutely and one of these things fails? Well, if it's this that fails, this is actually the nth term test, believe it or not. If not true, then the series diverges by the nth term test. So one of these things, in one of these three conditions, is already the nth term test, which we already know. The first condition is sort of like, well, we've already assumed we're dealing with an alternating series, so duh. So the only real question is this. And if that's not true, I'm afraid that you are screwed. You cannot do the problem based on Math 104 techniques. In fact, in some sense, I spent a heck of a lot of time on my PhD thesis trying to deal with a sort of series that does not converge absolutely and yet doesn't work with the alternating series test. And you have to do something just else. Maybe clever, if you're lucky. So, consider this series. Minus 1 to the n over n squared. A common mistake is to use the alternating series test on this. Sure, you can, and you will find that all three conditions work, and it shows you that it converges. But that is not the thing to do, because you don't know whether it converges absolutely or conditionally. The first thing to check is the absolute version. As I've said, first check the absolute version. If you do, you get the sum of just 1 over n squared, which converges by the p-test. So this converges absolutely. Don't use the alternating series test in that case because you already know it converges. The alternating series test does not tell you it converges conditionally. It just says it converges if it works. To really nail it down, you should have checked the absolute value first. And then don't do the alternating series test if the absolute works. I wonder, better do one more. Well, I don't know. Consider this example. Minus 1 to the n sine 1 over n. That's a good example as any. Converge or diverge? Well, first note that it's alternating, so there's negative terms. You might think the sine gives you negative terms as well, but it doesn't. Because n goes from 1 to infinity, 1 over n goes from 1 down to 0. 1 over n, 1, a half, a third, a quarter. And so sine of a number between 0 and 1 is always positive. So this is actually positive. It would be a different story if it was sine n, by the way. Sine n oscillates. But sine 1 over n when n is bigger than 1 doesn't. Nice, huh? Well, in any case, let's consider the absolute version. Which, of course, is the same thing as just sine 1 over n. After what I've said, this is positive. And we did the example of sine squared 1 over n just about half an hour ago. Just to remind you, we saw that sine 1 over n is asymptotic to 1 over n when n is large. After all, then 1 over n is small, and sine of the small number twiddles the same small number. So this diverges using limit comparison test with just 1 over n, which itself diverges by the p-test. So the series does not converge absolutely. Doesn't converge absolutely. On the other hand, if we look at, so try the alternating series test. It's clearly alternating because of the minus 1 to the n, and sine 1 over n is positive. Also, if you just consider the absolute value of the terms, which means ignoring the minus 1 to the n, which is sine 1 over n, this is clearly decreasing in n. I say clearly, I mean, if you really want to justify it, and it's not a bad idea, notice that 1 over n is decreasing from 1 down to 0 in the limit, and sine of x is increasing. So sine 1 over n is decreasing. That's fairly feeble, so maybe I better use a derivative. Let's just expand that over here, just to make sure. I claim sine 1 over x is decreasing when at least x is bigger than or equal to 1. Let's just differentiate it. dy dx, use the chain rule. You get cosine 1 over x times the derivative of 1 over x. Well, when x is bigger than or equal to 1, cosine of something between 0 and 1 is positive. So that's positive. 1 over x squared is positive, but the minus sign is negative. So this is negative when x is greater than or equal to 1. So that shows that the thing is decreasing. Finally, sine 1 over n, we just take the limit. These should be stars instead of dashes. Limit of sine 1 over n. Well, 1 over n goes to 0. Sine is continuous. So, since 1 over n goes to 0, sine 1 over n goes to sine 0, which is 0. So, that's what we want. All three terms, all three conditions are satisfied. Therefore, the original series converges conditionally, since it does not converge absolutely. All right, so that was a trickier example, but not very different than the other example. Sine doesn't really change a small number very much. So actually the solution is more or less identical to just minus 1 to the n times 1 over n. But you have to be a little more careful because of the sign. Doesn't do much, but does something. One quick example before we finish with series altogether. I'll talk about power series for half an hour. I'll just give you one very quick example. Consider this. Sum n equals 1 to infinity, 1 plus 1 over n to the n times minus 1 to the n. Alternating, sure. Try the alternating series test. No, try the absolute first. Actually, try the nth term test first. Save yourself some time. You could go down and you'll find that you get to the nth term test when you do the alternating series test. It's the third condition after all. But hey, limit as n goes to infinity of 1 plus 1 over n to the n is e. And the limit with minus 1 to the n in there does not exist. After all, if this quantity goes to E, that means the steps are going to E. On the other hand, this time with the minus 1 to the n, it sort of oscillates between E and minus E, or very close to E and very close to minus E. But in either case, it doesn't matter. The terms do not go to 0, so this diverges by the nth term test. You don't even need to do anything else. It diverges. Done. Without the minus 1 to the n, it would also diverge by the nth term test. E is just as bad as does not exist. The steps are not going to 0. So it can't have a hope of convergence. If the steps do go to 0, it might converge or it might diverge. But if they do not go to 0, either because they go to something else or they don't exist, the series automatically diverges. Nth term test. So it's a little bit of a subtle thing, but, not too many different options. Nth term test, absolute or alternating, or none at all, in which case we shouldn't have asked you the question. Not at least in Math 104. All right. Any questions about series in general? That's a pretty broad thing. Hopefully, get all those tests together. You need to do lots of practice, and you especially, after you get all the tests sorted out, need to do practice of just a mixed bag of series, and integrals for that matter, to make sure you know which test to use when. And at the beginning of, chapter, blah, 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 what is it? I forget, 23 is a summary of the tests that you should use. Or at least which tests, it's a summary of all the tests and when to use them. So check that out. It's an important topic. The next topic, however, is the important topic. This is the highlight of 103 and 104 in a way. So, power series and Taylor series. It's all one topic. And what I'm going to do in the next 30 or so minutes, well, I guess we started 10 minutes late, so I have 33 minutes, is to give you an overview of the topic. I'm not going to do many examples, but I am going to give you the whole idea of the next couple of weeks of what we're doing. Next time, I'll do a whole lot of problems, and it will probably spill over into the next week because there's a lot of different types of problems to worry about that I need to cover. So I'm just going to deal with, I call it theoretical, but it's really what is going on in this nice topic. So it's all in chapter 24, and then the problems are in chapter 25 and 26. Okay, so let me just start off by writing down a fact. E to the x is approximately equal to 1 plus x squared over 2 plus x cubed over 6 when x is near 0. There's a fact. Okay, what does it mean? Well, actually, if x equals 0, you get 1 here and you get 1 there. So it's not even approximately, it's perfect. But when x is near 0, small number, either positive or negative, this gives us an approximation. I'm not proving it yet, but let's just see what happens if I substitute minus a tenth. That's a pretty small number after all. So this says that e to the minus a tenth is approximately equal to 1 plus minus a tenth plus minus a tenth all squared over 2 plus minus a tenth all cubed over 6. And this is a simple enough fraction that you can work it out. You expand this to 1/100th and minus 1,000th, and you find out that it equals 5429 over 6,000. You could just do that by hand. But this is a fraction that turns out to be very close to this number, and yet that's almost impossible to compute without a calculator. This is quite straightforward. There it is. Now, if you actually change it to decimal places, I did use my calculator to change this to decimal places, and I found that this was 0.904837418 and so on. Now, that, of course, remember, the calculator does not give you the exact value. It only gives you the first 10 or 12 digits. Even if you use a computer and you get 1,000 digits, it goes on forever. So the best you can get out of a computer is an approximation. On the other hand, this one I can work out exactly. It turns out to be 0.90483 repeated. 33333. So it's not quite the same number, but it's really close. it's really close. It only differs in the 6th decimal place. Or I guess the 5th if you round up. This would be rounded up here to a 4. Okay, so it's very, very close. Now, it's quite useful. Polynomials, like the thing on the right-hand side, it's a cubic, are much nicer than non-polynomials. So, how did I come up with this approximation? Well, let's just review very quickly linearization, which we did earlier. It was a Math 103 topic. We took our function, in this case we have e to the x, and we took a point 0, 1, say, although you could do this at any point on the curve, and we said, what's the best line that approximates the curve near here? It's clearly not that. In fact, it's the tangent line, and that's the linearization. So this is the tangent line. Now the values, the heights, are very, very bad when you're down here. This is nowhere near there in height. But actually when you're close to 0, the heights are pretty close. At 0, they're perfect. But away from 0, if you're close, it's not bad. In fact, we even said that e to the x is approximately equal to 1 plus x. And 1 plus x is this linearization, as you can work out. What was the general formula for linearization? Well, you may recall that we wrote L of x in general is f of a plus f prime a x minus a. That hopefully rings a bell. Remember, this is the more general case where you have some old function like this, y equals f of x, and you pick a point A, and this line, that's the equation of the tangent line. L of x is this line, y equals L of x, the linearization. Okay, so you may notice that 1 plus x is very similar to what we had up there, 1 plus x squared over 2 plus x squared, x cubed over 6. In fact, it's the same constant term and the same linear term. We just don't have any quadratic terms or cubic, which we do up there. So the whole goal of this particular exercise, or at least this part of the topic, is that instead of using lines to approximate, we're going to use any polynomial. Could be quadratics, cubics. We'll see how to do any degree. But let's first look at quadratics. Do we have a question?
Yes.
Start shouting. I'm listening.
The x approximately equals 1 plus x plus blah, blah, blah. That's so on. That's not.
Well, so the question is, in that approximation, why did I stop at cubes? Well, that's a good question. It's more or less for example purposes, but you notice that actually I got a pretty good answer for that example of minus a tenth. Of course, we're going to be able to go further if we want, but you do have to stop somewhere if you want to avoid infinite series. Of course, we won't avoid infinite series, but more on that later. Let's just look at the next possibility. Suppose I take my function. In more generality, it might look something like this, and my point A, and instead of using a line, which might have looked like this, the tangent line, I use a quadratic. Well, if I use a quadratic, I'll draw it in blue, I may be able to get a closer fit, like this. It should still coincide, only perhaps at that one point. But you see, it will be a closer hugging fit, hopefully, to the curve. So it turns out that the best quadratic is given by this formula. F of a plus f prime a x minus a. Wait, that's just the linearization. There's another term, 1/2 the second derivative, x minus a squared. Now, that doesn't look exactly like a quadratic, but if you expanded it out, you get an x squared term, and everything else would be x's or just constant. So yes, it is a quadratic. In fact, it's a quadratic, though, in the term x minus a, right? Because it's 1, x minus a all squared. Still a quadratic in x as well, if you expanded it. Now, I'm just plucking that out of the air for the moment. I haven't justified it, I did justify the linearization in a way because you can work out the tangent, no problem. So where does this come from? Why is that such a good polynomial? Why is that the blue polynomial instead of some other polynomial like this, or a quadratic? Or, quadratics can look like they could even be lines or any parabola. Why do I get the one that hugs it really, really well and gives me a good approximation, the blue to the white? Well, again, it's a theorem. But I can give you an idea of why it's true without even referring you to the proof in Appendix A7, if you want to see it. Check this out. What's P2 of A? Suppose I plug in A. What do I get? Let's just do it down here. I'll save myself a little space. P2 of A. What do I get? I plug in A. What happens? This term goes away. This term goes away. Get f of A. What about the derivative? Let's take the derivative. A is constant, so this goes away. The derivative of x minus A is just 1, and then I have the coefficient f prime of A. On the other hand, the derivative of x squared is 2x. So the 2 will cancel out this 1/2, and I'll get f prime of A x minus A. So there's the derivative in general. What if I now plug in x equals A? Well, if I put in x equals A, this term goes away. And I just get f prime of A. All right, how about the second derivative? Let's take the second derivative. That's a constant, and the derivative of this is just 1. So I just get that the second derivative, I may have to zoom out to get all this in. The second derivative is just f prime of A everywhere. But in particular, the second derivative of A is of P2. The 2 stands for quadratic, by the way. Is the same as the second derivative of f at A. So this, remember, f is just some function, not a polynomial. It's like our e to the x. Whereas P2 is not only a polynomial, it's a quadratic. But it shares the value of the function, the 0th derivative. It shares the first derivative and the second derivative of f at x equals A. Nowhere else, necessarily, but at x equals A, the derivatives match. That's kind of nice. That's the only quadratic whose derivatives match. By the way, what's the third derivative of P? Well, this is constant, so it's 0 for all x. So it certainly doesn't match in general the third derivative, fourth derivative. In fact, P2 is a sort of distillation of all the information about the derivatives of f at x equals A, but only up to order 2, only to the second derivative. After that, forgets all about it. So we sort of grab the information. What do we know about f at A? We know the function, we know the derivative, we know the second derivative. Stop there, use that information, and that gives us P. We match all those things. So that doesn't prove it either, but it might give you some inkling of why it's such a nice approximation, because it shares a lot of information with f, particularly at x equals A. And near x equals A, that will affect it, and since everything is smooth, these things will be close. So let me give you the general case then. We'll extend the pattern, and so here is the general result. So this is our first main point. This is like the first big thing that I'm telling you. If f is smooth near x equals A, by which I mean not only does it have a derivative, but a second derivative, third derivative, fourth derivative, any number of derivatives that you like, let's just say. Then, of all the polynomials of degree n or less, capital N or less, the one which best approximates, so there's no better approximation, your function f of x near x equals a is, it's written P capital N of x. Sometimes they'll throw in a comma A or a colon A. I just prefer to keep it simple and write x here, and we pretend that we've already fixed A and we know what it is. So Pn looks like this. F of A plus the derivative f prime of A, x minus A, plus the second derivative at A over 2 factorial x minus A all squared. That's what we've already written, but I had a half there instead of a 2 factorial. It's the same thing. Then we'll have the third derivative over 3 factorial times x minus A all cubed. And I keep going up until the capital Nth derivative at A, n factorial times x minus A to the n. And so that is a polynomial that I hope you will become very familiar with. In fact, it's basically going to be required that you can just produce that from memory to do a whole lot of problems on this topic. So you'll become very familiar with it, as I said. Now, it does have a nice form in sigma notation, which looks like this. The sum from little n equals 0 to big N, it's the nth derivative at A over n factorial times x minus A to the n. And that clearly matches the previous expression, at least for 3 on up, even for 2. Notice when n equals 0, the 0th derivative is just the function f of A. 0 factorial is 1, and the 0th power is 1 as well. So when n equals 0, you just get f of A. When n equals 1, you get the first derivative divided by 1 factorial, which is just 1, times x minus A. So you do get that, and then all the other terms. Okay, so this is called the nth order Taylor polynomial after this dude Taylor, who investigated these things, of f about x equals A, or just about A. Okay, so that everything depends on A. If you want to investigate the behavior of that function up there somewhere else, you don't use the blue curve. You'd use a different blue curve. There's a different blue curve for every point. So it's only when you're investigating the behavior near a certain point, but not at it, that this becomes useful. Now, why do I say, oh, yes, nth order? Why don't I say nth degree? Well, it could be that this derivative over here, the highest derivative, might be 0. In which case, there's no nth degree term. There might be an n plus 1th degree term. That could be 0 as well, that derivative. So actually, it could be any degree less than n. And this is why I said of all polynomials of degree capital N or less. It may be that starting with the linearization, there is no better quadratic. An example of such a thing might be a function that looks like this. Okay, so the linearization is the tangent line here. But it's not clear that any quadratic will be better. If I took a quadratic like this, then it's sort of maybe better up here, I don't know, but it would be worse on this side. So actually, it may be that even allowing yourself to add a higher degree doesn't help. And that will happen if the derivatives that you add happen to be 0. So I say order n, or nth order, the degree might be less than n. It cannot be bigger than n. But order means degree equal to or less than this, or less than or equal to, I guess you normally say. Okay, so what do I have to say about Pn? Nothing that I haven't already said about P2. It's just that I'd better write it down to be general about it. All right, so the first thing I want to say is that the derivatives match. So I've already said that when n equals 1, you get the linear... Well, maybe I'll just say when n equals 1, all this stuff goes away and you just get the linearization. When n equals 2, you get that quadratic that I had before. And then, of course, when n equals 3, you get cubics, quartics, etc. So, derivatives match. Same thing. If you do a calculation, you can see that Pn of A is the same as f of A. The derivative is the same as the derivative. The second derivative is the same as the second derivative, but it also holds for all the derivatives up until the nth derivative. So it will work not just for the second derivative, but also the third, fourth, fifth, up until capital N. So all derivatives match up to n. Up to capital N. On the other hand, higher derivatives, so if I take the n plus first derivative, well, this is a polynomial of degree n or less. So if I take more derivatives, this is always 0. It's identically 0. Unlike f. Okay, it's just like f2. I took the third p2 rather. I took the third derivative of p2, and I get nothing because it's only a quadratic. So it has to stop somewhere. Pn is the distillation of all the derivatives of f at a up until capital N. So it's the same as before. All right. By the way, if f of x equals e to the x and a equals 0, what is p3 of x? Well, p3 of x in general is f of a is 0, plus f prime a, x minus a. Notice that I'm substituting on the fly x equals a. Plus the second derivative, I'm substituting on the fly a equals 0. That's what I meant to say. The second derivative, x minus 0 all squared, plus the third derivative over 3 factorial times x minus 0 all cubed. That's the definition of P3 of x, and I simply replaced a by 0. Well, if you work this out, f of x is e to the x. The derivative is e to the x. The second derivative is e to the x. The third, all the derivatives are e to the x. And when you plug in 0, you just get 1, right? F of, for example, f prime of x is e to the x. So f prime of 0 is e to the 0, which is 1. The same is true for f double prime, f triple prime is in the third, any of the derivatives. So if you plug this in, you get 1 plus 1 times x plus 1/2 times x squared, and 3 factorial is 6. So you get 1/6 x cubed. And that's exactly what I wrote up before. So that's where it came from. That's how I picked out that cubic. I used the third order general Taylor polynomial and then specified to a equals 0 and f of x equals e to the x. So this general formula that I've written up over here, there's an f to be plugged in and there's an a to be plugged in. If you know f and you know a, the only other thing is to decide how many terms you want, which is capital N. And then, in this case, I chose 3. But as you said, I could choose a higher number. I could choose a higher number. Now, I still have about 10 minutes left, so I'm going to move on to something that looks similar, but not quite the same thing. In fact, let's write down this approximation again. We saw that e to the x, e to the minus 1/10 rather, is approximately equal to, and I wrote up the fraction before, it's 5429 over 6,000. All right. So what can I say about this? Well, that's very good. We saw that they were very close. Now I want to ask you, how close are these things? Okay, a good way to understand this is to write that e to the minus 1/10 equals 5429 over 6,000 plus something, which I'm going to call the error. It's how wrong I am. Hopefully it's small. As we saw, it is very small. Okay? The point is that I can add a little bit onto this, and of course this could be negative, so maybe subtract a little bit, but I could change this by a little bit and get the correct number. Okay, so what I want to tell you is there is a nice formula for the error. It's not exactly perfect in a way because there's something strange about it, but nevertheless it's better than nothing, and it's pretty much the best you can do. So here it is. In general, this is what I like to write. I'm saying that f of x is approximately Pn of x. That's what I'm saying. Right? Pn of x is a good approximation to x, especially near x equals a. So what I'd like to do is write down f of x equals Pn of x plus a little bit, plus an error. But I better call the error something, and it's clearly depending on n. So I'm going to call this error Rn of x. And I say error, sometimes it's called remainder. It's what's left over after you take away the Pn. That's why it's an R and not an E. So R stands for remainder. So the definition then, Rn of x is f of x minus Pn of x, which you should think of as the true value minus the approximate value. Okay, so what I want to do is I want to show you the formula for this Rn of x and discuss it for a little bit. Let's see if there's any time left. I doubt there will be. All right, so what am I talking about here? I promised you a formula for Rn of x, and there is one, and it's called Taylor's theorem, which is a pretty big theorem as far as humanity is concerned. I'm serious. This allowed all sorts of things to be possible that were not possible before, leading to plasma TVs and the like, believe it or not. Quite a long chain there, but anyway, here it goes. Rn of x is equal to. It's very similar to the Taylor polynomial. It's the n plus 1th derivative over the n plus 1 factorial, x minus a to the n plus 1 to the n plus 1. In fact, if I just filled in an a here, it would just give you the next term in the polynomials. It would give you the n plus 1th term. But unfortunately, or perhaps fortunately, since not everything's a polynomial, I have to put in a mysterious number c. And you don't know what c is, which seems a little bit weird. But you do know something about c. It's between x and a. So if a is quite close to x, then this really pins down what c is. So, looks a bit weird. Let me write down the complete theorem then. F of x is Pn of x plus Rn of x. Well, that's just by definition. But just to put things in context, we have a formula for Pn, which by definition is the sum from little n equals 0 to big N, nth derivative at a over n factorial times x minus a to the n. That's just the definition. And then plus, so it's that sum, plus this remainder. Which I'll just copy. And again, c is between x and a. So any function that has at least capital N plus 1 derivatives, which are continuous, can be written as a decomposition of a polynomial of this particular form plus some bizarre remainder term involving a number c that you don't really know. So, why would you want to do this? Well, I will show you in the course of a few little observations, which will take the last 4 minutes that I have, and then we'll be done. But let me just make a few comments. First of all, why do I say c is between x and a? Why don't I just write a less than or equal to c less than or equal to x? Well, because sometimes x is to the left of a. So I could also, in that case, I'd have to write this. So I don't know how to say whichever one of them makes sense depending on a and x is true. So I just write c is between a and x. That's all that means. Now, what happens if n equals 0? Let's just put this in context here. Suppose n equals 0. Well, the p0 of x is just the first term, f of a. Whereas according to the formula, r0 of x is the first derivative at c divided by 1 factorial times x minus a to the 1, otherwise known as f prime of c x minus a. Okay, so according to this theorem, f of x is the sum of these two. It's f of a plus f prime of c x minus a, where again c is between x and a. So that's a special case of this theorem. Now let's rearrange this. Let's divide by x minus a and shuffle around. You can write it like this. F prime of c is f of x minus f of a over x minus a. Does that remind you of anything from Math 103 from the first half? F is a function. There is some number c in between x and a such that f... It's the mean value theorem. Exactly. Not for integrals, for derivatives. The original mean value theorem. So the mean value theorem is the special case just for linear, just actually for constants, for n equals 0 of this Taylor theorem. But that gives you an idea of why we can't say what the c is. We didn't know what it was in the mean value theorem. We just knew it was between x and a. So we don't know what it is here either. In fact, this whole theorem is just the mean value theorem on steroids. It's just a chunky, meaty version of the mean value theorem. But it turns out to be really, really useful. And I'm going to show you why in our particular case in the next few minutes. So bear with me. I know we started a little late in the room, but it hasn't quite been 2 hours on the video. So here it goes. I said, in fact, I just erased, that e to the x is approximately, or e to the x is approximately 1 plus x squared over 2 plus x cubed over 6. That's P3 of x with a equals 0. Well, let's write this exactly. This equals the same thing plus R3 of x. So it's no longer approximate. I'm going to add on the exact little bit of crack, that fill in the crack is what I'm trying to say. I want to add on crack. I want to fill in the cracks by adding on this small thing, R3 of x. What is R3 of x? Well, let's write this down. This is the fourth derivative at some number c divided by 4 factorial times x minus a to the fourth. But a is between, a equals 0. So I just write this. And what do we know? We know c is between x and 0. After all, we're taking a, that special number, in this example to be 0. Remember, the fourth derivative of e to the x is e to the x. Every derivative is. So this is exactly e to the c over 24 times x to the fourth. So actually, I can say that e to the x is 1 plus x squared over 2 plus x cubed over 6 plus e to the c over 24 times x to the fourth. And that is true for any x, for any number of x as it turns out. The only thing that I have to tell you is that c, again, is between 0 and x. And you say to me, what good is this? What good is this? After all, you don't know what c is, so how does that help you find e to the x? Well, it doesn't, but it helps you see how good you are. If I put in x equals minus a tenth, let's see what happens. So this is the final sort of point I want to make. You get e to the minus a tenth equals all this worked out to be, I better just get this right. What is it? 5429 over 6,000. But now I'm going to add e to the c over 24, and x is minus a tenth to the fourth. And if I work this out, I get 5429 over 6,000 plus e to the c over 24 times 10,000, so 240,000. Okay, so e to the minus a tenth, this mysterious quantity that I can't compute without a calculator, I can actually compute as 5429 over 6,000 plus e to the c over 240,000, where c is between 0 and x, but x is minus a tenth. So I know that c is in a very sort of tight little region between minus a tenth and 0. So I've got some idea of what's going on with this because c can only be between minus a tenth and 0. In particular, how large could e to the c be? It could be no more than 1, because when c is less than 0, this is actually a little less than 1. Did we run out of... Is it still taping? Okay, good. So this is actually less than 1. The biggest c can be is 0, so the biggest e to the c can be is 1, since e to the c is increasing. So actually, this error is between 0 and 1 over 240,000. So what's the moral of the story? The moral is, this is a very good approximation to e to the minus a tenth. In fact, the most wrong it could be is 1 over 240,000. So we are confident, without any calculator or anything like that, just from this theorem, that our answer, our approximation, is good up until about 1 over 240,000. Could be better, but it couldn't be any worse than that. Also, notice that since exponentials are always positive, we actually have to add a little bit to this to get the correct answer. You have to add something that's positive. This could be negative in principle, but e to the c is positive, 240,000 is positive. So when you add this, you get the correct value, which means this is an underestimate. It's too low, but it's not very low. It's an underestimate for e to the minus a tenth. Okay, so all this stuff is going to be tremendously useful for approximation. Next time, I'll tell you about the theory of power series and connect it to this, and then that won't take too long, maybe 10, 15 minutes, and then I'm going to launch into a whole bunch of different problems involving Taylor and power series.